Welcome back, AP Stat. This is part 4 of our 4-part series on chapter 14. We're going to start with the general multiplication rule. So like the addition rule with non-disjoint events, if two events are not disjoint, if they can happen at the same time, we needed to alter our addition rule to make a general addition rule. The multiplication rule will need an addendum for events that are not independent. So for dependent events, if the occurrence of one affects the probability of the other, the probability of A intersect B, the probability of A and B happening at the same time, is equal to the probability of A times the probability of B given that A has happened, all right? And this comes from the formula for conditional probability. You'll recall conditional probability of B given A is equal to probability of A intersect B, probability of A and B, divided by probability of A. So all we needed to do is multiply probability of A on both sides, and we get our formula for multiplication rule given dependent events. So now let's go to an example. A factory produces two types of batteries, regular and rechargeable. Excuse my lagging mouse. Quality inspection tests show that 2% of the regular batteries come off the manufacturing line with a defect, while only 1% of the rechargeable batteries have a defect. And just like that, my mouse fixes. Funny how that happens. Rechargeable batteries make up to 25% of the company's production. Okay, so we have two types of batteries, and both of those batteries have a small chance of defect. What is the probability that if we choose one of the company's batteries at random, we get A, a defective rechargeable battery, so we need both defective and rechargeable, and B, a regular battery, and it's not defective. So we need a regular battery, which we represent with B rather than R, and it's not defective, so the complement of defective battery. Think about how you would find the probability for these using the rules for conditional probability. Try this on your own if you would like, or you can just go right on ahead to the solutions. Okay, let's look at the solutions. The book does a good job with this one. We're going to let R be rechargeable and B be a regular battery. As I told you before, we're going to represent R as a rechargeable battery and B as just a regular battery. We can't use R for rechargeable and regular, so we got to be a little creative there, or the book had to be a little creative there. It's given that probability of R is 25%. That is in the problem, so probability of B, the other possibility, is going to be 75%, just the complement of that event rechargeable battery. So we're going to let D be defective, all right? It's given that probability of defective given a normal battery is 2%. That's up here. And the probability defective given a rechargeable battery is 1%, and that's what we get from here. So to start answering our questions, probability of rechargeable and defective. That's part A, defective rechargeable battery. Probability of rechargeable and defective is probability of rechargeable times probability of defective given rechargeable. Now the odds that we have a rechargeable battery is 25%. Probability of defective given it's rechargeable is 1%. Now note that is different than the probability of getting a defective normal battery. It's 1% less actually. These batteries are more reliable if they're rechargeable, interestingly enough. And that's going to be a very small likelihood, 1% of 1/4. Now going on to the second question. If 2% of the regular batteries are defective, then the other 98% are not. All right, so we use the complement of the event right off the bat here because we're trying to find the odds of not defective as part of our product. So if the odds of defective for a regular battery are 2%, then 98% are not defective. They work just fine. In other words, probability of not defective, that's what the little c is, complement of defective, so not defective, given we're talking about a normal battery, is 98%. So the probability of normal battery and its not defective, complement of defective, is equal to, what are the odds we get a normal battery? Well, that's 75%. And what are the odds we get a non-defective, so regularly functioning battery, given that we're talking about a normal battery that's not rechargeable? That's 98%. Multiplying these together, we get 0.735. So 0.25% of the company's batteries are rechargeable, and 73.5% are non-defective regular batteries. So there you have it. We're going to use another problem here. We're going to solve another problem using the general multiplication rule. And we are going to look at a circumstance in which we draw without replacement. And normally when we draw things without replacement, we're talking about cards, but here we're talking about Marshawn Lynch's favorite candy, Skittles. So you just bought a small bag of Skittles, whether at a Seahawks game or otherwise. Not that you could know this, but inside are 20 candies. How do they know? I don't know. 7 green, 5 orange, 4 red, 3 yellow, and only 1 brown. You tear open one corner of the package and begin eating them by shaking them out one at a time. All right, so we're eating these Skittles one at a time. That's convenient for our problem. What's the probability that your first 2 Skittles, one after the other, are both orange? So you're trying to find the probability of orange and orange given that you've taken an orange out and you haven't put it back. And then you want to find the odds that none of your first 3 candies is green. So you need to choose a not green, take it out of the pack, followed by a not green. Now you've taken 2 out of the pack, and then you need to choose a third not green. So there's a lot of conditional probability going on because each time you remove a Skittle, the probability of choosing another Skittle changes ever so slightly. So those are dependent events. See if you can solve these problems on your own, or you can just go right ahead to the solution. Choice is yours. All right, let's look at both of these problems. So getting 2 orange candies means I draw an orange first and then another one second, and there's 1 orange candy missing from the bag. So probability of 2 orange means orange first and orange second. Remember, we are getting these out one at a time, okay? So probability of orange first times probability of orange second given orange first. Why do I need conditional probability here if I'm selecting 2 oranges? Because I've removed an orange, that changes the probability for the second orange. Now, there are 5 oranges and there are 20 candies. So 5 out of 20, that's going to be my first probability. Then notice what happens to the numerator and the denominator. I take a candy out and my denominator changes to 19, and my numerator also changes to 4 because I'm trying to pick not just 2 candies, but 2 candies of the same color. So I start with 5 out of the 20, and then I only have 4 oranges left out of 19 for my second event. If I were to multiply, I would get 1 out of 19. The 4 and the 20 down here would cross cancel, and I have 1 out of 19. Now let's look at the second problem. None of the first 3 candies is green. So not getting any green ones means the first 3 Skittles were among the colors, all right? All the first 3 Skittles were among the colors other than green. So we have probability of 3 non-greens, and that's equal to probability of not green, not green, not green, all of them together. Now notice what happens. There are 7 greens, as we see up here, so there are 13 non-greens. So I have 13 out of 20. Then for the next one, I lose a non-green and I lose a candy. And then I lose a non-green again, and then I lose a candy. And this is some really messy multiplication. Leave it to the calculator. The book approximates it to about 1/4, which is rather interesting that's so close to a nice, easy value like that. So there's about a 25% chance I won't get any green Skittles among the first 3 that I remove from the bag without replacement. So when we don't replace, we need to recognize that we are dealing with conditional probability. So we need to use our general multiplication rule, not the easy peasy, just multiply the 2 values, basic multiplication rule. Now we're going to solve a problem using tree diagrams, okay? A recent Maryland highway safety study found that 77% of all accidents the driver was wearing a seatbelt in. Accident reports indicated 92% of those drivers escaped serious injury, defined as hospitalization or death, but only 63% of the non-belted drivers were so fortunate. Okay, so we have several things going on. We have seatbelt use and the outcome of an accident that we're considering. Overall, what's the probability that a driver involved in an accident was seriously injured? Now note, there are two ways in which you can get seriously injured. You get in an accident and you are wearing a seatbelt, or you're in an accident and you're not wearing a seatbelt. And we need to consider both possibilities. This implies both an or and an and. So there are two ways in which you can get seriously injured, hospitalization or death. And so there's a bit of or involved. But there's also some conditional probability, because whether or not you wore a seatbelt changes the odds of serious injury. So we're going to use a tree diagram for this, because this is a really messy problem, and tree diagrams, just like Venn diagrams, are your friend. So starting with the accident, there is a 77% chance that the person's wearing a seatbelt, and thus a 23% chance that the person is not wearing a seatbelt. So that's our first instance we're accounting for. Then we want to look at injured versus okay. If you wear a seatbelt, you have an 8% chance of being an injured person and 92% chance of being okay. And if you don't wear a seatbelt, the odds of injury, as you would predict, significantly increase, and the odds of being okay significantly decrease. So now we need to find products for all of these possibilities. Let's follow our tree in the uppermost sense. 77% times 8% is going to be 0.0616. 77% times 92% would be a little shy of 71%. 23%, following along, times 37% would be 8.5%. And 23% times 63% would be a little shy of 15%, say 14.5%. All right, so we found all the possibilities. These are the odds that you wear a seatbelt and you were really injured, seatbelt and okay, no seatbelt and seriously injured, no seatbelt and okay. And by the way, y'all should wear a seatbelt. So now let's find that probability. The probability of injured is equal to the probability of injured and seatbelt plus the probability of injured and no seatbelt. So we just follow our paths along. We see seatbelt and injured. The probability is 0.0616. No seatbelt and injured, the odds would be 8.51%. We add those together and we get 0.1467. So a little shy of 15% chance that you are injured in a car accident. All right, here's another example of using tree diagrams. We're going to revisit the battery factory. All the same stats apply. 25% are rechargeable, 75% are normal batteries, 2% of regular batteries, and 1% of rechargeable batteries have some kind of defect. What is the probability that a battery chosen at random from a shipment of the factory's products turns out to be defective? Again, there are two instances in which a battery can be defective: if it is rechargeable and if it is not rechargeable. Those are two different instances, and I should have said or. If it's rechargeable or if it's not rechargeable, okay, if it's just a normal battery. So again, we have some multiplication rules and addition in context. See if you can make a tree diagram to solve this problem, or just skip right on to the answer. All right, I'll assume we're ready to continue. So we're going to use the same labels as before. B means a regular battery, R means rechargeable, and D is defective. I should have said defect, opposite of effective, and OK is effective. It's a good battery. So here we go. We have our batteries, 75% are normal, 25% are rechargeable batteries, and of the regular batteries we have 2% defective, 98% okay. For the rechargeables, 1% defective, 99% okay. So we would do 75% times 0.02, 75% times 0.98, 25% times 0.01, and 25% times 0.99. So we get all of our possible paths here. And there are two ways of getting a defective battery. If we follow this path, which gets that probability, or if we follow this path, which gives us that probability. So it's just addition from there. So what they do, which is nice here, is to check to see if the probabilities all add up to 1. This is the textbook doing this, and they do all add up to 1 or 100%, and they cheer. Cool. Now to find the probability of defective is probability of original battery, regular battery, and defective, plus probability of rechargeable battery and defective, and that adds up to between 1 and 2%. 1.75% of all batteries produced at the factory are defective. So as I've said, tree diagrams are your friends, especially if you have messy problems like this, where there are several ways in which you could fulfill the event of being defective. All right, we're going to close out our lesson with one additional detail, reversing the conditioning, right? So we're going to go back to the concept of conditional probability and explore a little nuance of that. Suppose out of the ballpark 300 high school students at FCA, there are 80 freshmen, 15 of whom play basketball, okay? Suppose there are 30 players on the JV or varsity basketball teams, right? So considering all of that, consider the two probabilities. Probability of basketball player given freshman and probability of freshman given basketball player. So in the first probability, we're finding the odds of being a basketball player given that we're only dealing with freshmen. And then we're finding the probability of freshmen given that we're only dealing with basketball players, okay? So for our first one, how many freshmen are we dealing with? Well, there are only 80 freshmen out of the 300 students. And of those 80, 15 are basketball players, all right? So 15 out of 80 would be our unreduced fraction. Now you flip the conditioning around and we deal with all the basketball players. The basketball players, there are 30 of them. And again, if we are saying what are the odds that we are considering we're only dealing with basketball players, what are the odds that we are dealing with the freshmen? Well, 15 of the freshmen play basketball either on varsity or JV. So 15 out of 30, or 1/2, would be this probability. Yeah, those probabilities are not the same, which means if you change the conditioning, then you are going to change the probability most likely, okay? If not certainly. So reversing the conditioning often produces different results, as we have seen here. One result that's certain, though, is that you have homework. Have a great day.